Here we are, lesson 3 of our known nonsense A-level physics lessons. And today's lesson is about photons. A word that you may have heard before at GCSE level, but your understanding of photons possibly isn't all there because photons aren't very well explained at GCSE level. And truth be told, not very well explained at A-level either. So when you first learn about light at GCSE level, you learn about what's called the electromagnetic spectrum. Let's spell it right. Magnetic spectrum, which is just a way of categorizing different types of electromagnetic waves, starting with those of the longest wavelength, which we call radio waves. These have a wavelength typically in the order of more than 10 centimeters, sort of around about a meter, that sort of thing. That's the wavelength we're talking about there. In fact, we should probably label this, shouldn't we? So can I grab this text and move it over to the right slightly? Yes, just like that. And I could label this bit here wavelength. Let's just choose a pen. Wavelength. And I'll choose this one here. And what should I say here? Category. Let's just say type, rather than category of radiation from the electromagnetic spectrum. There we go. And a line down the middle. So we start with radio waves. Those are the waves with the largest wavelengths. And there's no upper limit to them. What I'll do is, rather than writing a full range each time, I'll just write, say for the next one, it'll be a millimeter. It'll be anything that is more than a millimeter for microwaves, but obviously that doesn't include radio waves. So microwaves, they are radiation, electromagnetic radiation, where the wavelength is a little bit more than 1 millimeter, but less than 10 centimeters. Just like that. Well, that's what your mobile phone uses for communication. You can use it in a microwave oven to cook food. Microwaves. Right. Then we have infrared, as used in a conventional oven, what we might call an infrared oven if we're feeling a little bit weird. These radiations are anything where the wavelength is a bit bigger than the visible range, and the visible range starts at around 700 nanometers. Although perhaps that's a little bit on the large side, but we'll go with that. So one significant figure number, it's probably about right. Oh, I forgot the bigger than symbol. Better put that in there, otherwise people will get all upset. Bigger than about 700 nanometers. Right, lovely. Now, infrared radiation is also used in things like night vision cameras. They can be sensitive to infrared. We can also transmit information with infrared with remote controls. And then we have the star of the show, visible light. Now, visible light has a wavelength between 700 nanometers and, well, about 400. You might even say 450 would be a bit more correct, but let's put 400 nanometers in there. So it's actually quite a narrow band of wavelengths, the visible part. The reason why we evolved sensitivity to that is because that's the radiation that gets through the atmosphere most easily. So you can see the advantage of evolving to be most sensitive to that. Then we have ultraviolet. That's radiation where the wavelength is even smaller than visible light, even smaller than violet, hence the name, but it's still bigger than about a nanometer. A nanometer is about 10 atoms in diameter, roughly. So let's draw a line through this. So, that's ultraviolet. Then we go towards X-rays. And really, X-rays should be at the end of this electromagnetic spectrum, because all of the parts of this electromagnetic spectrum so far are emitted when we have radiation emitted from electrons in the orbits of atoms. And when those electrons de-excite, they emit all these parts of the electromagnetic spectrum. So there's a bit of overlap here between ultraviolet and X-rays, really. So we could say it's from about a nanometer, maybe even a little bit more than a nanometer, down to maybe even a picometer or femtometer. Let's go picometer. So usually they're bigger than 1 picometer. Remember, pico times 10 to the negative 12 meters. I might have to write that down in my notes if I haven't remembered these prefixes, but I can do that later. And then we have the odd one out, which is gamma radiation. What makes gamma radiation so different is that gamma rays, spell it right, gamma rays, spell it right, gamma rays do not come from electrons being de-excited. They come from the nucleus of atoms, and so they tend to be even more energetic than X-rays. And yeah, I mean, anything that's small, we could actually say this is something that's smaller than about a nanometer. We're looking maybe in the order of angstroms, that sort of area. So in the order of angstroms. An angstrom is symboled by this A with a circle over it, like that. So we can start saying, what do these prefixes mean? Centi means 10 to the negative 2. Milli means 10 to the negative 3. Nano means 10 to the negative 9. Seem to have missed micro there. Then we get pico, so 10 to the negative 12. And angstrom is 10 to the negative 10. It's worth knowing. We also have micro, which would be 10 to the negative 6 meters. And we have femtometers, which would be 10 to the negative 15 meters. But they're not included in this list. So that's our electromagnetic spectrum. And I've said wavelength, but what on earth is wavelength? Well, we know from GCSE what wavelength is. It is the distance between two adjacent peaks of a wave. Wavelength is part of our equation, which sometimes gets called a wave equation. And because it's not quite the wave equation, I'm going to call it the GCSE wave equation. Now is not the time for me to go into the wave equation proper. There'll be time for that when we are doing the topic called waves. C equals, we usually go F first, F lambda. Like that. You'll see some textbooks will not use an F, they'll use the Greek letter nu for frequency instead, and that's okay. But we're using F. That's what's more common at A level. So that is our GCSE wave equation, and our lambda is our wavelength. As you probably remember, that's the wavelength. And what's F then? Well, F is the frequency, which we think of as how many waves per second will pass us, and C is the wave speed. Frequency we can measure in a unit called hertz, wave speed meters per second, and wavelength meters. And there we go. So that's our GCSE wave equation, and that's what we mean by wavelength. Now, in classical physics, if we had brighter light, we would understand that as a larger amplitude of electromagnetic radiation, and therefore more energy being delivered per second. So we understood that the energy of an electromagnetic wave was related to the amplitude of the electromagnetic wave. And we could draw our electromagnetic wave like this. So let's start with our axes. There's the y-axis, here's the x-axis, and let's have a z-axis coming down at a funky angle like that. like this. So there's my z-axis. Maybe this would be my electric field, like this, in the x direction. Maybe this is the magnetic field in the y direction, but let's actually color code them. And this will be slightly different to the way it appears in textbooks, but that's for good reason. Unfortunately, in textbooks, they very often draw these the wrong way around, such that the Poynting vector would actually be in the opposite direction to the vector, the unit vector along the direction z. But you don't have to worry about that yet, because you know what? It's early days. We've just started our A-level. So this is a wave, and we could draw it as a sine wave, or at least we can try to draw it as a sine wave. It's not easy to draw a sine wave in 3D, where you're showing the oscillation in the horizontal plane, but that's what I've tried to draw there. And the magnetic part is going to go down like that, then up, then down, then up, then down, then... Oh, I missed. Oh, should we try again? It goes from here to there, to there, there. Something like that. I think that's about as good as I'm going to be able to draw at the moment. It's a bit wonky at the beginning, but it doesn't matter. That's our electromagnetic wave, consisting of an electric field part and a magnetic field part oscillating with the same frequency in phase with each other. What do I mean by in phase? The answers are coming when we study waves. You're going to get a lot of that in A-level, of what do we mean by this? Oh, the answers are coming later. This whole equation is going to be explained later as well, so don't worry too much about it. What they do in the A-level textbook is they usually draw the a magnetic field in a horizontal axis, which is what I've used for the electric field here, but they'll say positive is to the left, and it just looks like a mess. I mean, technically it's fine, but it looks like a bit of a mess. So that's what we think of as electromagnetic radiation. And if we have higher frequency radiation, that means a smaller wavelength radiation. If we have lower frequency radiation, that means a larger wavelength, because of that equation C equals F lambda that you can see in the middle of the screen. Well, that was fine, and for a very long time, that equation was all we needed to understand light. However, there was an experiment called the photoelectric effect, which the wave theory of light could not explain. So photoelectric effect will come later when we do quantum physics, but I'll mention it here, so it's in your notes. Photoelectric effect cannot be explained using wave theory of light, let's say. Electromagnetic radiation is what I really mean, but let's just say light for brevity. So how do we explain it? So Albert Einstein, 1905, he solved the problem of electromagnetic radiation causing electrons being emitted from the surface of metals. He solved the problem by using the work of Max Planck, which I've heard his name pronounced Max Planck, but I just can't bring myself to say that. Max Planck. Max Planck. So Max Planck's idea of energy was that rather than having energy in a wave determined by the amplitude of the wave, and he was actually looking at vibrations within crystals and things, but rather than that, he said that the energy is proportional to the frequency of the vibration instead. And that led to the equation, we should probably put that down here. This is the work of Max Planck. Excellent name. So this actually leads to the energy of the vibration being equal to some constant multiplied by that frequency. And again, you'll see some textbooks and notes that use nu as the frequency. That symbol is the Greek letter nu, but we're not going to use that. We're going to use an F, because that's what usually gets used at A-level. What Albert Einstein did is he looked at that and said, well, what if everything is like that? What if light is like that? What if light comes in discrete packets? discrete packets, and we can call them photons now, and those photons each have an energy E. So E is energy of each photon, just like that. And then F would be the frequency of the radiation of, let's say, EM radiation. Hopefully we don't need to write down what EM means. I could put up here EM is electromagnetic, just so it's in the notes. And H is a constant, is Planck's constant, probably capital P because it's a proper noun. Planck's or Planck's constant. And you can measure it. And I've done experiments where I've measured it. You can find them on my YouTube channel. But Planck's constant is about 6.63 times 10 to the negative 34 joule seconds. Interestingly, it has the same units as the units for action, but we don't do action in your A level. So if that is the energy of each photon, then what about the amount of energy delivered by a light source, maybe a laser? So if I have a source of light, let's say laser power, what's going on there? Well, there we might say that we have n photons being delivered in every t seconds. And we can say that this is equal to n, the number of photons per second that are delivered by this laser. Photons per second. Remember, photons are just a packet of electromagnetic radiation, a packet of energy, where the frequency of the radiation determines the energy of each packet. I don't want to call it a particle of light because it's a bit of a naff way of describing it, really. Right, so we've got that. So remember that power is equal to the amount of energy transferred per unit time. Again, we shouldn't have to define each of these terms, but in our notes, it is definitely worth doing so. Energy transferred, and this is duration or time. So the energy that's being transferred is what? Well, the energy that's being transferred by our laser is going to be equal to the number of photons multiplied by the energy of each photon, which is hf. And so that's going to be equal to n, the number of photons per second, hf. Notice we use lowercase and uppercase letters in our physics A level, and we have to be clear with which one is which. So if n photons per second are being delivered, each has an energy E equal to hf, then the power of our laser would be nhf. And that's as far as we need to go with this session. You can use that equation, P equals nhf, to work out how many photons per second are emitted from a light source. We can now calculate the energy of a single photon. That's what E is. And we know what a photon is. A quantization, that just means a discrete amount. A quantization of electromagnetic radiation. Maybe I should write that down somewhere so it's in our notes. Photons are the quantization or discretization, making it discrete, not continuous, of electromagnetic radiation. There we are. That's what photons are. And so concludes this section all about photons. In the next lesson, it's going to be about particles and antiparticles. Ooh, very exciting.